Welcome back. Let's get started with some trigonometric graphs. Start with our creed and then get moving because we got kind of a crazy day today. So, today's a new day. I can read and remember well. I can develop my viewpoint and apply it correctly. I have eyes to see, ears to hear, and a mind to understand. It might not be easy, but it is worth it. All right, here we go. So we're going to be looking at trigonometric graphs. More specifically, the tangent, the cotangent, cosecant, and the secant. So all the ones that aren't sine and cosine. But we're going to be using sine and cosine to graph each of these. And I really want to show you how the graphs of sine and cosine pretty much determine everything we're doing today. So let's get started. So if we look at this, what they've done at the beginning is just given you the four graphs of the day. They've said, hey, we're going to apply some shifts to these four graphs, whether it's left, right, up, down, stretch, compression, or reflection. We're going to apply some shifts to these graphs and see what happens as those happen on the equation and on the graph. It's important to note we've got vertical asymptotes happening now, which we didn't have with sine and cosine, and where those asymptotes happen. That sometimes the graph starts at a 0, or 0, 0 more specifically, and sometimes the graph doesn't. Sometimes the graph has an asymptote at 0, 0. So note that's the main key thing for our stretches and compressions to note is which ones are which. Which ones start at the origin or the y-axis and which ones have an asymptote at the y-axis. All right, so here we go. Let's get started. So to start us off, they just give us a basic tangent function and say, look, I already gave you the tangent function. There it is, right? And if we were to graph the sine and the cosine and with our knowledge, so we know that the sine function has a classic period of 2 pi and an amplitude of 1. So that by our last section, we could basically graph the sine function right there, right? That blue function. Given that that last point is 2 pi, we can't really see it. And by that last section again, we could graph, let's not do red, let's do green. We could graph this green function as the cosine function, right? So like this, start here. We know that it's got to cross 0, go all the way down to -1, cross 0 again, go all the way back up to 1. That last point's probably a little bit short, but that's just because they didn't give it to us. And then what we see happening here is we know the rules of tangent mean sine over cosine, right? So they mean blue divided by green, right? Sine over cosine. So if we look at this point, is that red line blue divided by green in every point? Right here, if this point were a little bit better, we would see all three of them intersect there, which is pretty cool. So if we divide the blue by the green and they're the same thing, it would end up at 1 where they intersect. If we divide the blue by the green, we should divide blue over green. So this one, at this point right here, we would get 0 over 1, right? And does that make sense that we have 0 over 1? Well, the red line looks like it's at 0. So if you just take your time and go through all 16 special points on the unit circle, divide them, you'll get your tangent, right? We've done that before when we did trig properties. So that's kind of what we're seeing today with this tangent graph. If you don't like looking at it that way, this is the graph right here. It kind of looks kind of like that cubic function, but the better way to think about it, it has asymptotes at pi over 2 and negative pi over 2. So let's see. As we move forward, we're going to say, what is this 2 doing to this tangent? This 2 right here, that 2 is probably giving it because it's on the outside, right? It's kind of like our old amplitude. But if you don't like that either, it's a vertical, and because it's on the outside, it's a stretch, right? It's a vertical stretch by a factor of 2. So it's basically like grabbing that thing and stretching it by a factor of 2. Now, if we vertically stretch our asymptotes, they don't really change, right? So I'm going to go back up and look at the tangent asymptotes and just redraw them on the graph because the asymptotes can't get stretched. You try to stretch a vertical line, it stays exactly the same, right? Okay. But what we do have is the special point of tangent. We know that well, let's start with 0. So the tangent of 0 is, I don't know, let's think about this. You don't have to plot these points because we're applying shifts, but the tangent of 0 is the sine of 0 over the cosine of 0 times 2 at the end, right? And the sine of 0 is 0, so that's 0 over 1 times 2, so that's just 0. So your tangent stays at 0 because if it were vertically stretched, it wouldn't really change, right? But you know what would change? That normal 1 would change to a 2 because it got stretched by a factor of 2. So I'm going to plot my point up, plot my point down, and then be happy with that as our reference points for the graph, since everything else would be off the graph, right? And then if you like the way you drew that, you can copy it over and move it to each of the other points. Boom, boom. It's okay if it's a little off the graph like that. I'll put it over here, and you can see how this tangent function repeats with a cycle, with a little bit different of a cycle though, right? Every time it repeats, how far did it travel? This is just a note we're making that we'll see in a little bit. How far did it travel when it repeated? Well, it didn't travel 2 pi like normal, it just traveled pi. We talked in class about why that is, but it's got a, oh, that goes further. Boop, boop. It's got a cycle t equals pi over k instead of 2 pi over k. It's kind of interesting. The parent function is a cycle of pi, or a period of pi. All right, well, here we go. This is not too crazy. This is just saying vertically reflected. So if we vertically reflected or reflected across the x-axis, will the asymptotes change? Probably not. Will the zeros change? Absolutely not. But what will change? The directionality of this thing, right? It was looking like a normal cubic function. We flip it, kind of looks like the opposite cubic function. And that's just applying a transform. If you want to go ahead and plot some points to see that that's true, feel free to plot those points. I would never be upset with you graphing a few points to see whether you like what you did or not. So there we go. That's the tangent function. The tangent function's pretty good. The tangent function's not too crazy. All right, here we go. This is where we talk about that. I already kind of said it, where t equals pi over k. I believe this is supposed to be cotangent. I'll fix it on the draft. And basically they're saying, hey, the period's a little bit different now. Instead of going 2 pi over k, we're going to go pi over k, and it's going to repeat that much. If you want the explanation from class, we talked about how the tangent is positive, negative, and then the same identical positives based on reference angles off of the x-axis. If you look at the unit circle and you think about the positives and negatives, maybe you could help you with that, because you know tangent is sine over cosine, right? Tangent sine over cosine, and you got a positive over positive. You got a positive over negative. You got a negative over negative. Oh, and those are the same. Those corners are the same, right? A negative over negative and a positive over positive are the same. And you got a negative over a positive, which is the same as the other corner. And that's why it repeats every half, not every whole cycle, right? Every half unit circle, we've got our tangent repeating, not every whole unit circle. If that was too fast, come to office hours, we'll talk through it really slow about it. Or maybe I'll post a separate video just about the unit circle and these graphs. So sketch each graph. We've got a tangent. Now we've got an internal shift instead of an external one, but I'm just going to grab that internal shift. I'm going to say t equals pi over 2, because that 2 is my k. Not too crazy. That's my new cycle. Did it shift left? Did it shift right? Up, down, stretch? Nope. That's the only thing that happened. So my asymptotes better stay the same. Let me graph those real quick. The asymptotes didn't change. Right? Boop, 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 boop. Sorry about this. Oh, the asymptotes did change. Why did I do that? The cycle changed, right? So let's take that whole thing and watch this. We'll use it with this moving instead of redrawing thing. So what happened to the period, right? Well, the period got half as big. So it better be half the size, right? Each of those gaps that used to be 4 little squares, now how many little squares should they be? 2, right? And so we're going to move all of those lines in and horizontally compress this. So I'm going to grab my mouse. I'm just going to horizontally compress this until it's half as big. Okay. Looks like I did it on the right side. Let's do it on the left side and see what happens. And then move it over. Oh, I need it to be a little bit bigger. Boop. This is harder than I thought it'd be. Sorry in advance. Oh, I need to be a little bit smaller than that. There we go. Okay. So when those blue gaps used to be pi over 2, or pi long, now how long are they? Well, they're pi over 2 long now, right? Not pi long. And did anything change about our graph? Nope. So we're going to draw the same shape. We're going to know that about halfway through it should cross 1. If you're thinking about that in your brain, that about pi over 4, we should cross through 1. And you could duplicate that if you want to across the board to get yourself the rest of your function. Duplicate it, put it on that other side. A lot of times when you're working these problems, it won't ask you to draw every single one. It'll say, hey, draw one period or one cycle of this thing, which would be way easier than having to draw it 10 times like there. All right, here's where it gets wild. Here's where they add both things, right? So here's what they've done. They've added a horizontal shift. Boop, 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 right? Horizontal shift. Which way? Remember, it's opposite. So we're thinking opposite in our brain. So we're thinking goes to the right, pi over 4. Okay. But they've also added a, what's that? What was that called? That was, it's inside the function, right? It's inside a tangent, and it's horizontal. So it's getting compressed or stretched. We'll think about it's opposite of what you would think. So it's a big number. So we're going to compress it, right? So that's like a horizontal compression. That 2 is going to feed our formula of t equals pi over 2. Pi over k. Sorry, pi over k, which is pi over 2. If you want to see where that comes from. And then we're going to go and graph our points. So we've got a horizontal shift by a factor of pi over 4 and a period of pi over 2. Okay? So what we need to look at is which one should we do first? There's no right or wrong answer, but you need to be careful to apply them both. So I'm going to apply the squish first since it's similar to what we just did above. Literally, it's the same squish or horizontal compression. So here's my compression happening, squishing it to this one basic pi over 2. And if you want to look at it, you can see that if you draw that line, how far does it travel? It travels pi over 2. Okay? But then we've got a horizontal shift of pi over 4. Well, how many squares is that on our graph? Looks like it's 1 square. Every pi over 4 it travels. So it's just 1 square shifted to the right. So I'm going to take that whole thing I just drew, and I know it's hard on your paper, so I said I don't know which one's right to do first, and we're just going to shift it over by pi over 4. So that was our shift. If you want to see that shift happen, we did it right there. And then I'll draw my normal tangent, remembering that it probably crosses 1 at pi over 4. Or pi over 4 away. All right. Oh, I don't need to copy all that, just this. We're going to duplicate it, and we're going to see it happen a bunch of times. I'll just do it 3 because you've seen me do this already. All right. Here we go. Let's get to a little bit more challenging of one. Actually, I'll leave this for you to do so we can fly through this and you can get to the other problems, but I will help you set it up. To set it up, we got to identify that this 3 is inside the parentheses, not outside. So technically, we don't have a horizontal shift because it's being applied to both. So the little shortcut or the sneaky thing here is to set it equal to itself, but to get a common numerator, it's like get something you can factor out. So that 3x minus, if you know 3 pi over 12, it's technically the same thing as pi over 4. So we've just adapted that a little bit. And then to say, well, that's the same thing as 2. I wrote cosine, sorry. Cotangent. 2 cotangent. Let me check about, okay. 2 cotangent. And what I'm going to do now is I'm going to factor out a 3. And then x minus pi over 12. And I'll leave you to graph it, but what you're going to see here is we've got a, let me write them small. We've got a vertical stretch times 2. We've got a horizontal compression times 3, which means that our period is pi over 3, right? That's the distance between asymptotes. And then we've got a shift, or a horizontal, not stretch, but shift, where it just slides over this way to the right, pi over 12. Sometimes it helps to change your axes. Sometimes it helps, I think in class we change this to pi over 3, and so on and so forth. Feel free to change your axes if you need to, make it a little bit easier. If that's pi over 3, that would make that 2 pi over 3 because it's twice as long, which would make that 3 pi over 3, which is just pi, right? And that would make that 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, I think. Yep. So if you want to do that, that's not a bad way to look at this problem. Might help you graph and get a little bit better of a graph in there. So then you do the same thing on the other side by converting this to a negative pi over 3 and so on and so forth. All right? let's hop down to secants and cosecants. And I want to teach these in a really simple way that we're going to use our old tools to graph the new graphs, okay? So they do give us this formula for period, which is awesome. I really like it. They give us this amplitude, which again is awesome. But we've already learned that. Remember we learned about amplitude and period with the sines and the cosines? So what I'm going to do is I'm going to help us look at labeling these the normal way, the old way, drawing that graph to help us draw our new graph. Sounds complicated? It's not. Watch this. I'm going to take cosecant and I'm going to say, what goes with cosecant? Cosine or sine? Question mark. Well, remember it's kind of flip-flop what you would think. It's not cosine, so sine goes with cosecant. So what I'm going to do before I even start this cosecant graph, before I go up and look at what it's supposed to look like, I'm going to rewrite the function y equals 1/2. I'm going to help to graph a reference function or a reference trigonometric graph. It's going to help me a lot. You'll see. Okay, so now I'm going to graph that function, which is great because it helps us review the sign, but it's also nice because it's going to point out everything we need to know. So let's call this, for our sake, a reference graph, which we're going to graph. And I'll just do it in red so we don't get mixed up about the colors. So reference graph. We know where sine starts, boop, right? And we know that this sine has an amplitude of 1/2 because that's sitting out front, right? So let's just call this 1/2. 1/2, which makes this 1, right? So then remember when we did our sine, we drew kind of like a dotted line right there. You don't have to, but I like to because, so that's negative 1/2. It helped me know how tall and how short my sine wave would go. And then 2, remember 2, so that was a amplitude, and 2 was a horizontal compression, also known as a phase shift, which turned it into 2 pi over 2, which just meant pi. Pi is our full wave. So it means I got to get back to myself at pi. So that gives me my sine wave. If that's tough to do, go watch that section again and practice these sine waves, because it's really important that you can graph a sine wave, any sine wave, just by being given the function just like that. But the point of this wasn't to graph a sine wave, right? This isn't our problem. Hang on, let me finish this. Boop, 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 boop. Sorry, I'm going pretty fast on that graphing, but that's because we've already done it. So, that was a bad point down there. Okay, actually, here, let me finish. Boom. Okay, here we go. So that's the red graph. That's our reference graph. That's going to help us. So now what I'm going to do is step 1. I'll use blue since we've been using blue for asymptotes this whole day. Is step 1, put an asymptote at every x-intercept. You know, you're saying, why? Why put an asymptote at every x-intercept? Well, because we remember cosecant is 1 over sine, right? And if sine is 0, because that's called x-intercept, roots, zeros, x-intercept solutions, they're all the same. If x is 0, that gives us 1 over 0. And that's bad, right? We can't have 1 over 0, so that's an asymptote. So at every single x-intercept, I'm going to draw an asymptote. That's just our new methodology of graphing these secants and cosecants. Right there, every x-intercept I see, I'm throwing one of these blue asymptotes, just like before. Yes, there's a lot of them. Yes, that's okay. Okay, so step 2. So that was the blue step. Now I guess step 2 would be the green step. Green is good. So step 2 would be at the peak and the trough, graph the inverted shape. And to learn the shape, let's go look. Let's go up and look at it, okay? At the peak and the trough, graph the inverted shape, or the inverted parabola-looking shape that is the crest of the wave. So if we look right here, boom, there is the inverted wave, right? If we think about our wave where it should be happening, technically our sine wave should, that's too big, 1 second. Technically our sine wave should look like this, right? So we're graphing the inverted sine wave at every peak and trough. We're just going to turn around and graph it inverted, approaching those asymptotes, right? The peaks and the troughs tell us where to go, and the peaks and the troughs tell us which way to go. because we're going to invert them. That's what I said, the word inverted or the 1 over. So I'm going to take every peak and trough. So let's start on this first one right here. Plot that point. Actually, we could just plot all the points. Those are on our graph. Those points on our new graph. And then we're not going through the red. We're going the opposite direction because it's flipped 1 over, right? So we're just going to plot just like that. And knowing and keeping in mind that our green function is our function. The red function is not the function, right? The green function is the function. The red function was a reference to help us graph it. Cool? So the green function is y equals cosecant, 1/2. All right, let's do one more of these. I'll do it kind of quickly because it's very similar. So secant, what's the reference angle? Do it in red. 3, cosine, remember they're kind of flipped, 1/2 of x. So let me plot that real quick. We're starting at 3, right? We start up there. How long does it take us to get back to 3? Let's find out. T equals pi over 1/2. 2 pi over 1/2 because it's a cosine, right? Equals 4 pi. That's the period. That's how long a cycle takes. So we don't have 4 pi on this graph, but the whole graph is 4 pi wide. So let's see. If it takes a whole 4 pi to get over, we're going to end up at 2 pi to get down to the -3 right there. -3, which means we're going to cross at pi and -pi and -3 at this -2 pi. There's my cosine. Okay? So it kind of looks like that. Now what we're going to do is we're going to take that and remember, exact same steps. The x-intercepts make our vertical asymptotes. The peaks and the troughs give us where to draw our graph at. There's a 3. And we are done with our graph. Let's go up and see. Does that look like the secant graph? Secant centered around the center. Secant center. It does look a lot like it, just stretched out. All right. Hopefully that's helpful. Hopefully that's not too wild. Make sure you're practicing these problems at home, really learning about how secants and cosecants interact with sine and cosine. That is the best way. If you're looking at that, what's on the screen right now, the best way to do it is to graph your reference angle first. And then if you're taking a test and you want to erase it just for safety, you can erase it and say, look, there's my graph. But I think it's really helpful to have that reference wave so you know where to graph. Okay? Thanks for watching. I'll see you in class. Have a good day.